So, first of all just read this problem. So, it is written that which of the following statements are true. So, first of all we choose p bigger than 0 and we have to find the limit. First of all, first one is log x by x to the power p, second one is again same one. So, it says first one says 0, second one says infinity, and third one is e to the power x divided by x to the power p, and fourth one is the same one, and again the limit is either 0 or infinity. Now, this is a simple problem. So, I start with this simple problem. So, when I write exactly this 1 and 4. So, when I taught that which one? Uniform continuity, right? Uniform continuity, then I told this one, right? So, first of all you should understand here. So, what is what is going faster, right? So, again I am explaining that one. So, first of all you should understand between these, say you have x to the power p for any p bigger than 0 and you have log x and another is e to the power x. So, you have three type of function. So, you should understand that which is going faster. So, actually this is going faster than this in this way. That means x to the power p is faster than log x for any p, even you can take that p very close to 0, but positive, and also if you choose a very large p, still it is that e to the power x will be faster than x to the power p. Even you can use that L'Hopital rule as well, right. So, first one, if we take limit x tends to infinity log x by x to the power p, then we know it is a infinity by infinity form, right. Now, we can use that L'Hopital rule, then we get, so the derivative of log x is 1 by x. So, we have x to the power minus 1 and second one will be x to the power p minus 1, right. So, that will be limit x to the tends to infinity 1 by x to the power p. So, that is 0, right. And similarly, we can, so the second one is wrong, so this is true, and similarly when you solve that one, then even if you have a large number of p, you can just use that L'Hopital rule again and again until we get the lower part is that lower part vanishes kind of thing. Okay. Then by applying many times of or finite number of L'Hopital rule, you can find the limit is infinity. Okay. So, this part is simple. Now, go to the next problem. So, this one. Now, it says let f be a monotone decreasing real valued function on R. Okay. Now, which of the following are true? So, first one is limit x tends to a f of x, that is limit of the function f at x equal to a always exists for each a. Now, second one says f is unbounded, and third one says if a less than b, then the right hand limit at a is less than equal to the left hand limit of b, and fourth one says g x equal to e to the power minus f x is bounded. Now, tell me what will be the answer of this one. Okay, someone is saying that repeat example 1 again. That example 1 is simple, you have to just use L'Hopital rule. So, that example 1 is very simple, you just try, that is very simple. Just use the L'Hopital rule. Okay. Okay. So, for this one, obviously, so many people give answer C and some of them gave C, comma D. Okay. So, that means, so many of you are giving that C. So, can you prove that C? So, you should know the proof, right. So, can you prove the C? So, let us come from the first. Okay. So, first of all, if you have any monotone non decreasing sequence, or you can say monotone increasing sequence, that is actually the same concept, and we have to show that limit at some point may not exist, right. So, for this example, so a is not true, because we can choose this function, say f x equal to just 0 when minus infinity less than x, say less than 0 and equal to just 1, where 0 less than equal to x less than infinity, right. That is a step function with one step. So, it is up to this, and then from this we have this. Okay. Okay. So, this one taking, and we are not taking this. Okay. Right. So, we have a jump. So, in that case, the limit at 0 does not exist, right. So, we can rule out this one. Now, for the second one, it says f is unbounded. Again, the same one says that, right, by again the same example, here f is bounded, right. The image of f is just 0 and 1. So, therefore, f is bounded. So, again this is ruled out. Now, first rule out the d. So, g x equal to e to the power minus f x, it is bounded or not. So, again if we take f x equal to just x, then my g x will be e to the power minus x, but it is unbounded in R, right, because limit x tends to minus infinity, g of x, that is infinity. So, again this is also ruled out, right. Now, how to prove this C? Obviously, C is correct here, but you can get any other options as well, right. So, how to prove that C? Now, you should know for this one. Okay. So, what is the definition of right hand limit and what is the definition of left hand limit, right. Now, if you do not apply anything, see from this you can only see that limit x tends to a plus f of x, that is you can only say it is less than equal to f of b, and also you can say that f of a, that is less than equal to limit x tends to b minus f of x, right, and also you have f of a less than equal to f of b. See, from this you cannot say anything about that, right, but we can guess that this is true. So, for this, to prove this, what we need to find? So, first of all we need to choose one C between a and b. So, let us choose a real number C such that a less than C less than b. Okay. Since a less than b, so we can always get this one. Now, what is my right hand limit of this? Now, so take the interval a comma c. Okay. Now, if we take any x n from this interval a comma c, and x n converges to a, that's mean, so this is my a, this is my c, this is my b, right. Now, we are taking this interval, and what is the right hand limit at a? So, we have to choose any arbitrary sequence x n which is in this interval and converges to a. Now, as x n converges to a, right, now limit or you can say x tends to a plus f of x will be just limit n tends to infinity f of x n, and that is less than equal to f of c, right, because f of x n less than equal to f of c, right, because f is a monotone non decreasing sequence. So, what we are doing, we just first of all take a and b, we take an point c and we choose some x n from this one such that x n converges to a, right. Now, we know that x n is less than c, right. So, f of x n is less than equal to f of c, since f is a non decreasing sequence, right. So, therefore, the limit of this one, that is the right hand limit, is less than equal to f of c. So, you can say that this is less than equal to f of c, and by similar approach you can say that this is greater equal to f of c, and then you can say this one. So, this is the proof of C. Okay. Right. So, if you take f as a constant sequence, constant function, it will be non decreasing as well as bounded. Yeah, it is fine. But why do we need that? Okay, for that a and b, yes, for a and b we can rule out by that one. Good. Okay, this is clear, right? So, this one also simple. Now, move to the third problem. So, here it is given that P be a polynomial of real variable x, which is of this form, and suppose P x has no root in -1, 1. Okay? And it is also given that if P of -1 equal to 0. Now, then we have these options. So, first of all, f of 1 equal to 0, f of 2 is bigger than 0, f of 3 equal to 0, and limit x tends to infinity, P x equal to infinity. Now, just note that, so when you solve a problem for your examination, okay, this is going, okay, anyway. Now, when you solve a problem for examination, then it is fine, you can just rule out something, you can use some shortcut trick, right. But when you solve for yourself, that is for to prepare yourself for examination, then you should solve each and everything. If you believe that something is not true, you should give one counter example, and if you think something is true, you should give one, so you should prove precisely. Okay. Now, first of all, so what is this one? So, there is problem with my camera, where it is, okay, fine. So, can you give the answer of this one? So, first of all, it is given that P x has no root in the open interval -1, 1. Okay. So, you have to know this fact, and also you have to understand that the coefficient of this term here, it is 1, and also the coefficient of this, that constant term, is also only -1. Now, we know that product of the roots, so we know what is the product of the roots, it is that plus minus of this constant term, right. Now, since here the constant term is -1, therefore, product of the root will be plus minus 1. So, depending on n is even or odd. Okay? Fine. Now, the product of the all root is plus minus 1. Okay. Now, suppose if you have a root, say r, such that r is bigger than 1. Now, from this, can you say that you should have at least one root such that r is less than 1? You can, right, because the product of the all roots is only plus minus 1. So, therefore, if you have one root which is bigger than 1, then you must have at least one root which is between 0 to 1, right. But it is given that if Px,
Hello.
yes,
The product of the roots is minus 1.
sorry, I did not get what.
So you wrote here product of the roots is plus minus 1.
Huh.
But the last term is minus 1. So the product of the roots is only minus 1.
Is it not depending on plus that even or odd? I forgot that one.
Yes, sir, depending.
It is, I think it depends
Yes,
on
sir,
that
just
odd,
depend
right?
on-
It is something minus 1 power n some kind of thing, right? Then constant term. Because if you take x,
Sir, we don't know the value of the x, so we can't take it as
yeah,
positive
so
or
that is the
negative.
reason, no? Suppose you have px equal to x minus 1. See, the root is 1, right?
Yes, sir.
Okay.
Thank you, sir.
So anyway, so you just need that plus minus 1, that modulus value is 1, that is fine. But the main aim is if you have a root r which is bigger than 1, then you must have another root. So then you must have another root, say r2, such that r2 is that one, right? Otherwise that product will be not 1. Fine. Is it clear? Okay. Now it is given that polynomial does not have any root in there, minus 1 and 1. So what does it mean? That means you do not have any root which is bigger than 1. In fact, you can say that this one. So if you have a root such that mod of r1 less than 1, then you should have another root r2 such that mod of r2 is less than 1. Okay, otherwise the product will not be plus minus 1. Okay. Now since there is no root in minus 1 comma 1, so that means there is no such root. Okay. So therefore the only possible root will be plus minus 1, or you can write plus 1 or minus 1 with repetition. Is that clear? Yes? Say something?
Yes, sir.
Yeah,
Yes,
you
sir.
can write. Okay. See, someone has written that minus 2 can be a root. No, minus 2 cannot be root. See, if minus 2 is a root, then remember that the product of all roots should be plus minus 1. That means you must need another root which is lies between minus 1 and 1, so that the product will be minus 1 and 1. The product will be equal to minus 1 and 1, minus 1 or 1, right? Now it is given that P has no root between minus 1 and 1. So therefore you cannot have any root such that modulus value is bigger than 1. Okay. So that's mean this term will be ruled out. Which one? This. So P3 cannot be 0. Okay. So you cannot have any root on which is bigger than 1 or less than minus 1. So therefore the only possible roots will be plus 1 or minus 1. So therefore fx will be, that is px will be of the form only x plus 1 say some r and x minus 1 say m, where r plus m equal to n. Okay? Now what if there is, if 1 is not a root? Now, if 1 is not a root, then minus 1 will be the only root, right? Then minus 1 will be the only root. So, therefore, p x will be x minus of minus 1. So, x plus 1 power n. Now, in that case you can see that the last constant term, so p x will be something x to the power n, and then that will be plus 1. The constant term will be plus 1. Now, again we have a contradiction. Now, it is given that the constant term is minus 1, right. So, therefore, 1 should be a limit, should be a root. Right. So, this is true. Now, it is given that minus 1 is a root and also you have 1 is a root. So, therefore, in this case you have that r and m both will be bigger equal to 1. Okay. Now, what will be my P2? What will be P2? Now, just put the value of P2, that will be 3 to the power r and this one, right. This is 1 and we know that r is bigger equal to 1. So, this is also bigger than 0. So, this is also 2, right. And also since it is, so the constant power is just 1. Now, if you take limit x tends to infinity, then p x will be also infinity. So, this is also true. So, we have A, B, C, these 3 are right answer for this question. Okay. So, A, B and C. Now, is there any doubt on this? I can repeat if you ask.
No, sir.
Fine it is for everyone?
Yes, sir.
Yes, sir.
Okay. So, if this is, if some question you feel that something is fine, at least write someone that yes, okay, then I can go to the next. Otherwise, see, I cannot see your face, so I do not know your expression, right. So, it is better, even I cannot see my face as well, because I am presenting on slide. Okay. Now, move to the differentiable. Please explain option 2. Okay, okay, okay. See, this is simple. So, we just proved that here p x equal to x plus 1 and x minus 1, and where r and m both are bigger equal to 1, because we proved that if 1, it is given that minus 1 is a root, and we proved that 1 should be a root as well. So, therefore, it should be of the form of this, and now p of 2 will be 3 to the power r, where r is bigger equal to 1. So, therefore, this is just bigger than 0. Okay. So, r is just a natural number. Okay. Now, move to the problem number 4. Here my I is minus 1, sorry, 1 union 2, okay, only 2 number, 2 point set, and phi x is defined as distance of x comma I. That means this is the definition of distance. Okay. Now, they ask that phi is discontinuous at some point on r. The second one is phi is continuous, but not differentiable at x equal to 1, that is only x equal to 1. Second one says it is continuous, but not differentiable at x equal to 1 and 2, and third one says, sorry, fourth one says f is continuous, but not differentiable only at x equal to 1, 2 and 3 by 2. Okay. I know this one, so you feel this is good, this is easy, right. many of them already write the answer. This is D, exactly the answer is D. But before going to the proof, I just want to define the differentiability. Okay? So, I know all of you know the term differentiability, but still I want to explain because I will use that fact. So, you should know maybe right. So, I know that you people know this the definition of differentiability. So, anyway, it is just a recall for you. So, I just give the definition. So, now you can unmute, right. So, could you please just tell me? So, I shall define the differentiability at a point geometrically. So, can you someone unmute and tell me that differentiability, what is the differentiability at some point with some tangent kind of definition? Yes?
Sir, if we have unique and
If we have unique
tangent at a point, then we say that this at this point function is differentiable.
Okay. Now, what is the definition of tangent?
Slope of the tangent line.
Yeah, no. What is the definition of tangent?
Sir, tangent is a line which touches the curve at a single point.
Okay.
Inclination of tan theta. If theta with the inclination, then tangential is a differentiation.
Okay. I did not get what you were saying.
That is dy dx equal to tan theta.
Yeah, but we are now defining, right? So, we will define the differentiability in terms of tangent, right? So, you cannot define tangent in terms of differentiability. Well, so, yes?
Sir, tangent is the limiting case of the chords between 2 points on the curve.
Yeah, exactly. That is actually the proper definition of tangent. Good. So, first of all, we can write what is a definition of tangent first of all. Okay. So, what is, so I am not writing the proper definition, I am just giving you. Now, suppose you have a curve, okay, you have any curve. Now, suppose you want to find tangent at this point, okay. Now, what you will do? Now, suppose this is your x. Now, what you need to do to find a tangent of a curve, then you just have to choose any other point closer to this x, first of all, say some x plus h, okay, and just draw the line between x and x plus h, say this one, or you can choose a different color. This one, where just h is bigger than 0. Okay. Now, this line, now suppose this line is my LH. Okay. Now, then write tangent at x is limit h tends to 0, that LH. That means you just choose, if you want to find the tangent at x. So, first of all choose a h positive and then take that x plus h. Okay. So, actually in our case it is not the x, it is just x comma f of x, and it is x plus h comma f of x plus h, this one. Okay. Now, you have a line, call this line as LH, then that right tangent at x is a line L you can say LR, that right tangent, which is the limiting value of this one. Okay. Now, similarly, you can define a left tangent. Now, similarly, suppose again you have a curve, this one say. Now, suppose you have x, again you can choose h positive, say h positive. Now, take say x comma fx, say x minus h comma f of x minus h, that point, right. Now, join this line. Okay. Now, call it is some, or you can write it is LR, call it is LH, something kind of this. Now, then left limit, sorry, now left tangent at x, that will be limit h tends to 0, L say left h. Okay, so you will have many lines and you just take h tends to 0, then you will have a single line. So, if that is exist, okay, then this is called a left tangent. Now, we can define a tangent. So, sometimes some books they say that left tangent and right tangent, they have a concept of that left tangent and right tangent, and they call both of them as tangent. But some of them also refer both are the different one, okay, and they says that no, tangent is unique, and if that is the left tangent and right tangent are equal. Now, here, so we say f dash x exists if the left tangent and the right tangent both exist and equal. Okay? And in that case, that f dash x will be the slope of the tangent, and that is slope of the tangent. Okay? So, if you have left tangent and right tangent, if both exist and if both are equal, then we say that the function is differentiable at that point, and the value of that f dash x, we say it is just the slope of the tangent. Okay? Now, from this is clear that if f dash x is bigger or equal to 0, what does it mean? Suppose f dash x is bigger or equal to 0 for all x.
Monotone increasing.
Right.
The curve is
Inclination of the theta is negative.
I don't know what is do mean by inclination. Anyway, so that's mean.
So inclination of theta is sukho kon jetake
Okay. Anyway, I don't know that term. Sorry. So that's mean, say whenever we have f dash x is bigger than 0, that's mean it is not the parallel to x, right? So that's mean it is just the theta is bigger than 0, right? So that's mean you can say that the curve of this function, it is increasing, right? Now, suppose at point, suppose f dash x is 0 at some point. Now, you can say that at that point, that's you know that what is the slope, right? And if you have that f dash x is bigger or equal to 0 for all x, then you can say that f is monotonically increasing. And if you have f dash x is strictly bigger than 0 for all x, then you can say the function is strictly increasing function, right? And similarly, the function, if f dash x is less than or equal to 0, then the function will be monotonically decreasing sequence, and if f dash x is strictly less than 0, then the function will be strictly decreasing function. Okay. Now, this is clear from the definition. Okay. Now, again there is another concept. So, that is mean, so I know many of you know this one, or at least everyone I think know this one. So, who knows the definition of differentiability. So, now if you have a reflection of a curve, now suppose f x equal to mod x, that means you have a reflection, right. So, this one. So, that means see what is my left tangent in this case. So, you choose a point here, right, and choose a point this one,
minus 6.
right. Now, if we take that line will be the minus x, and it is true for all h, right. And if we take limit that h tends to 0, still we will get this one. So, this is my left tangent, right. Now, similarly, if you choose any point here, then if you get, then we will have this one. So, we will have this is right tangent, right. So, therefore, the left tangent and right tangent are not equal in this case. So, therefore, we generally call that f x equal to mod x is not differentiable at x equal to 0, right. So, that means whenever you have a function where you have a reflection, so this kind of thing or this kind of thing, then you can easily say that. So, it is not differentiable at this point, it is not differentiable at this point in this way. Okay. Now, we come to this problem. So, this one. Now, if you know, if you just apply this definition, so we can split the whole domain into few parts. Now, if you take any x which is less than 1. So, that means we will count when you say x, right. If you take x less than 1, then we have to, since we are taking that infimum, then we will take x equal to only 1, right. We will not take 2, because that is the lower distance. So, that means whenever you have x less than 1, then your phi x will be mod of x minus 1, that is this is the infimum, and this will be 1 minus x. And obviously, phi 1 will be 0, because your x is 1, then the distance is 0, fine. Now, if you have this one, that is 1 to 3 by 2, then again that if you from this one, that if you have x between 1 to 3 by 2, then that x minus between x minus 1 and x minus 2, that x minus 2 is the infimum, that is the slower one, right, smaller one. So, therefore, again this and this is actually x minus 1, because it is bigger than x is bigger than 1. And again when it is 3 by 2, then both values are same. That means x minus 1 and x minus 2 both are same, you can take any one and you will get a value that is half. Again, if x is between 3 by 2 to 2, so you have this one, that is between x minus 1 and x minus 2, this is the smaller one, right. So, we have 2 minus x, again phi 2 is 0, and for 2 bigger than 2 less than x, when is x is bigger than 2, again 2 is x minus 2 is the most smaller one, and we have this. So, therefore, if you draw the graph, that graph will be, suppose this is 1, so this is 2, suppose this is 3 by 2, so it will be this kind of function, kind of w, right. Now, you can see that we have 3 reflection, all of these are line, right. So, this is not differentiable, these 3 points. Okay. So, in this case, everyone already write that one. So, this is the right one. Okay. So, any question regarding this?
Sir, please explain how phi of x becomes 1 minus x for x less than 1.
Okay. Now, look at the definition. What is the definition? So, what is a distance function? It is says infimum of x minus y, and it is depending on y, that is y belongs to I, right. Now, in our case that I has only 2 values. So, in our case phi x will be infimum, means we have actually minimum because we have only finite value. So, it will be minimum of mod of x minus 1 comma x minus 2. So, this one. Now, if you have x is less than 1, that is left side of 1, then that distance will be the lower one. So, this is not right. Now, if you have x is less than 1, then phi x will be mod of x minus 1. So, we are writing that. And mod of x minus 1 is 1 minus x, as x is less than 1. So, we need a positive value, right?
Okay, sir.
Fine? Okay. Now, since this is just a collection of few lines and we have some reflections, so from this we know that it is not differentiable at these 3 points, right? Even if you want to prove this one, you can easily prove. You can find the left hand derivative at 1 and right hand derivative at 1, then you will get 2 different values. Okay? So, one can find that left hand derivative at f1, it is not equal to that right hand derivative f1. That means the tangent wala definition. Okay? Okay. Now, we move to the next problem, that is the similar to this one. Now, we have I is 0 1, that is instead of only 2 point we have whole interval 0 1, and again we have phi x equal to distance of x comma I. Now, we know what is the distance function. Now, the question is, can we say that phi is continuous, and what about the differentiability of this? Now, obviously, what will be my phi in this case? Yes. So, can you give a just quick answer of this one?
Continuous but not differentiable.
Yeah, which point it is not differentiable?
0 and 1.
0 and 1.
0 and 1.
Right. See, these are the very simple problem, right? Now, again if you want to find that f phi x, you can easily calculate that. Now, phi x will be, now when is x say minus infinity to x less than 0, then it will be that mod of x minus 1, right? Now, it will be mod of x minus 1 means, sorry, x minus 0. So, mod of x minus 0. So, this one, that is mod x. Now, since it is a negative value, so we have minus x, right? Now, when we have 0 less than equal to x less than equal to 1, then the distance will be the 0, because the value x itself lies in I. So, therefore, it is 0, right? Now, if the value, that is if you take x is bigger than 1, so therefore, it will be mod of x minus 1, right. So, it will be just x minus 1. So, 1 less than x.
Question phi of x, what is written phi of x equal to?
Distance of x comma I, we have given the definition, right. So, this is the distance.
No. Phi of x equal to,
Huh.
what it is written that supplementally.
No, it is distance between x comma I.
Okay.
Distance. Okay. Now, again you can find that this function will be this one. So, this, then 0, then this. So, you have 2 reflection. So, this point 0 and 1, it is not differentiable. Okay. So, these are very simple problem. I know you all know this one. See, during that competitive exam you face this kind of problem only. So, if you have just little bit of concept, you can easily solve those. Now, we have this one. Now, here also we need the concept of that reflection. Okay. Now, we have f x equal to mod of cos x plus mod of sin of 2 minus x. Now, we have to show that if it is differentiable or not on these sets. Now, how to? Now, can you give a quick answer of this one? A and C. Wow, this is just a quick answer. Good. Okay. So, whenever you have this kind of function, just remember that where we are facing problem. Okay. So, we are facing problem here when you have that cos x and sin x. So, what is the graph of this cos x or sin x? See, we know that graph is of the form this one, right? This type of graph. So, depending on sin x as cos x, you have some 0, pi, pi by 2 in this way, right? Now, what is mod of sin x and mod of cos x? Now, if you have this graph, then you will have this one, this. So, this actually the same points we are talking about. Okay. So, this, so this way. Right. So, that is mean where the function gives the 0 value, then the problem will occur. So, then we will have a reflection of mod of cos x and mod of sin x. Now, we know that now we have to choose the sets where that is sin x or cos x gives the 0 value. Now, again we know that cos 2n plus 1, that is odd number of odd product of pi by 2, that is 0, we know that, right. So, here we will have a reflection and also here we will have a reflection, right. So, therefore, between these 2 points on these 2 sets, the function will not be differentiable, right. Fine, it is. So, many of you have already given the answer. So, I think it is fine with everyone, right. Okay. Now, go to the next problem. So, this one. Now, here it is given that capital F is a collection of functions R to R and f x minus f y is less than equal to k times x minus y power alpha, where alpha is some number which is bigger than 0. Okay. Then we have these following problems. So, it says that every function of this one is continuous, every is uniformly continuous, every function is differentiable, and it says that if something is differentiable, then also it will be in f. So, many of you already are giving the actual answer. So, you do not have to, okay, someone says please show the previous slide. Taking a screenshot, you do not have to take screenshot. So, I will share the slide with you. So, through the WhatsApp group, I shall send you the slides. Okay. So, you do not have to take the screenshot. Oops. Okay. So, first of all, now this is a condition. So, f x minus f y, that modulus value is less than equal to k times x minus y power alpha, where alpha is some number, positive number. Now, this term is called that Hölder continuous, okay, and this condition is called also Hölder condition. Now, obviously, we can easily show that it is uniformly continuous, right, because again if we go to the definition of uniform continuity, we know that if we have some x n minus y n, if that is converts to 0, now then we must have f of x n minus f of y n that is converts to 0, right. So, therefore, this is true. So, therefore, we have this uniformly continuous. Now, we also know that any uniformly continuous function is also continuous. Okay, someone is written it is Lipschitz. No, it is not Lipschitz condition. Lipschitz condition says that alpha equal to 1, okay, and this is called Hölder continuous. So, if you take alpha equal to 1, then it will be Lipschitz continuous. Okay. Now, obviously, so 1 and 2 are true, obviously. Now, you have to give a counter example for C and D. Now, can you give a counter example for C and D? So, first of all, it says every f. Yes.
Mod x.
Okay, fine. Yeah. Now, for C, you have a counter example mod x, right? So, mod x is not differentiable at 0, but this satisfies this condition, okay, for alpha equal to 1. So, this is not true. So, we can take f x equal to mod x, right. And the second one says, no, last one says that if f is differentiable, then f must be in f. Now, again, see, now you have to just give a counter example in this way, that you have to give a function which is differentiable everywhere, but not uniformly continuous. Why? Because if you give a function which is differentiable but not uniformly continuous, then it should not satisfy this condition, right? Because this condition says the function will be uniformly continuous. Now, we can just, in this case, we can choose f x equal to say just x square. Now, this is differentiable and not uniformly continuous on R, right. Now, since this is not uniformly continuous on R, so therefore, it should not satisfy this condition, because we know that this condition implies that uniform continuity. So, this is D is also not true. Fine.
Sir, how we can say that f of x equals to x square belongs to capital F set?
No, it is not. It says if f is differentiable, then f belongs to f. Here f is differentiable, but f is not in this set, because this another example is just e to the power x. You can take another one, f x equal to e to the power x. This is also differentiable, but not uniformly continuous. So, you have to just choose one function which is differentiable, but not uniformly continuous. So, therefore, we can say that this is not in that set, because any element from this set should be uniformly continuous, right. So, as I told you, so whenever you are solving a problem for your NET or for your JAM, you should solve each and every possibility. So, even it is clear that one, if you know, even it is a single choice problem, still you should try to find counter example for the other choices as well, because then it will improve your brain. Okay. Now, from this, can you give some property of alpha so that we can say that it is differentiable? Now, what if
alpha greater than 1,
If alpha is
then
greater than 1, then f is differentiable.
yes. Now, what if again if you take alpha equal to 1, then again if you that f x equal to mod x example will work, right? Because again you just check from this in this point of view as well. Now, suppose if your alpha equal to 1, then f of x minus f of y by x minus y, that is modulus value is just less than m, sorry, k, I have written k, right. Now, since modulus value is just less than a number k, so that does not say anything that if you take limit x tends to y, that will exist or not, right. But if you have alpha bigger than 1, then you have some x minus y, some alpha minus 1. Now, in this case, if you take limit x tends to y, then you will have f dash y that will be equal to 0, right, because that term will be converts to 0. Or I should not write in this way, we can write this x just limit x tends to y, then we will get f dash y that is equal to 0 for all y, right. So, in other words, you can say that your function f is constant function, right, because its derivative is just equal to 0. Okay, so there is another problem. Now, this says this one, so this is also simple, you can just trivially verify this one. Okay, so I just take this problem again from the NET question paper, I think. Okay. Now, this one is also simple. Now, if you have r, f r to r, we are following this function, and we have to check that f is continuous or f compose f equal to f. Okay. Now, again, first of all, if you take a1, okay, so first one. Now, if we take x equal to 2, now it is easy to check that first of all that a is continuous. You can just have to check the values at 1 and minus 1. So, at both points this value is 1, right. So, this is continuous. And if you take x equal to 2, then f of 2 will be 4, right, and f compose 2 will be f of 4 equal to 16. So, that means obviously f compose f not equal to f. Okay. Now, for the b and c, you can easily verify that one. Now, again for the d, you can check that at x equal to minus 3, this is not continuous, because the left hand side will be minus 1, that left hand limit will be minus 1 and right hand limit, all of have given that correct one. So, this and this, so this is we ruled out, right, by this one, and also here we rule out this one. So, many of you have given that right answer of the